Namaste. In this video, we are going to discuss about the linear homogeneous recurrence relation. In previous video, we have discussed about the types of recurrence relation. So let us discuss about the linear homogeneous recurrence relation. Let us consider a recurrence relation as like an equals to c1 a n minus 1 plus c2 a n minus 2 plus dot 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 to ck a n minus k, and its solution is supposed as a n equals to r power n, and the characteristic equation or characteristic equation, it is also known as characteristic equation. So Rn equals to c1 Rn minus 1 plus c2 Rn minus 2 plus dot 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 ck Rn minus k. Okay, so let us consider a simple two terms expression an equals to c1 an minus 1 plus c2 an minus 2. Then its solution is considered as an equals to r power n. So since there are two terms, we have used r square only. Okay, so the characteristic equation is r square minus c1 an minus 1 minus c2 an minus 2 is equals to 0. And let us suppose that it provides two roots r1 and r2, and suppose that they are distinct or they are different. Okay, so if they are different, then our solution is an equals to alpha 1 rn r1 power n plus alpha 2 r2 power n. But if the roots are same, that means r1 equals to r2, then we have the solution a n is equals to alpha 1 plus n alpha 2 whole multiplied by r power n. Okay, so let us consider an example. Okay, so what is the solution of the recurrence relation an equals to 5 an minus 1 minus 6 an minus 2 with the initial condition a naught equals to 0, a naught equals to 3 and a1 equals to 5. Yes, so let us consider the solution of this recurrence relation as an is equals to r power n. Yes, by our method. Yes, so the characteristic equation, since there are two terms, so the characteristic equation is r square minus 5r, so minus becomes plus 6 equals to 0, and we factorize it, we get r equals to 2 and r equals to 3. Since they are different root, yes, or distinct root, so our solution is written as an equals to alpha 1 r1 power n plus alpha 2 r2 power n, and that is an equals to alpha 1 r1 is 2, yes, so 2 power n plus alpha 2 3 power n. So the given condition is when n equals to 0 a naught equals to 3, when n equals to 1 a1 equals to 5. So that is when n equals to 0 a0 is equals to alpha 1 plus alpha 2, because 2 power 0 is 1, 3 power 0 is 1, so alpha 1 plus alpha 2. When n equals to 1, then we get a1 equals to 2 alpha 1 plus 3 alpha 2, and we know that a naught equals to 3, so alpha 1 plus alpha 2 equals 3, a1 equals to 5, so 2 alpha 1 plus 3 alpha 2 equals to 5. So by solving these two equations, we get the value of alpha 1 and alpha 2. Yes, and we get that as minus 1 and 4. So our solution is an alpha 1 into 2 power n. Yes, that means alpha 1 is minus 1, so minus 1 into 2 power n is minus 2 power n, plus alpha 2 is 4, so 4 into 3 power n. So this is our required solution, and it is also known as explicit formula. Okay, the solution is also known as explicit formula. So let us consider another example. Okay, derive an explicit formula for Fibonacci series, and we know that Fibonacci series, the sum of two previous term is equals to third term. Yes, so an equals to an minus 1 plus an minus 2, where the first term is 0 and second term is 1. So we consider this recurrence relation, and we know that by the process the solution is considered as an is equals to r power n, be the solution. So characteristic equation of this can be given as r square minus r minus 1, because there are two terms, yes, n minus 1 and n minus 2, so we consider as highest power as 2. So r square minus r minus 1 is equals to 0. So this is characteristic equation, and by solving this equation we get r equals to 1 plus minus square root of 5 divided by 2. Since they are distinct root, yes, 1 minus root 5 by 2 and 1 plus root 5 by 2, they are different roots. So we consider the solution as a form of an is equals to alpha 1 r1 power n plus alpha 2 r2 power n. And by solving the equation as previous, we get this value. Alpha 1 is equals to 1 by root 5 and alpha 2 equals to minus 1 by root 5. So by substituting the value in the previous equation, this equation, we get the solution as like this. Okay. So in this way, we have solved the linear homogeneous recurrence relation. Okay. And in next video, we will be solving non-linear homogeneous recurrence relation. Okay. It is the type like, I think, n equals to 5an minus 1 plus 6an minus 2. If this terms, then this is linear. And non-linear consider another part, that is 2 power n or 7 power n. That means the n variable is not linked with a. Okay. So this is the example of non-linear homogeneous recurrence relation, and in next video we will be solving this type of recurrence relation. Okay, thank you and bye bye.